Okay, we're going to develop the thin wall pressure vessel model. At the same time, we're going to apply it. So we have this round tank that is quite large. It's 6 foot in terms of its outer diameter and has a very thick wall thickness of 2 inches. Right? The internal pressure is 1200 psi. That is an enormous internal pressure in a tank, and that is why we're also seeing quite a large wall thickness. Right? And so we're going to ask here, what's the factor of safety with respect to yielding if the yield stress is 36 ksi for what we call the longitudinal and the hoop stresses. All right, so let's get into how this all works. And the first thing we want to do is just do a double check to see if the thin wall pressure vessel theory even applies. So let's check our diameter to thickness ratio. And we've got a diameter, an outer diameter of 72 inches, right? So that's crucial. That's the outer diameter. The inner diameter, well, we got a wall thickness of 2 inches. So we got to subtract off 2 of those wall thicknesses to get all the way, all the way across. So that would be 68 inches for the inner diameter. And it's, you know, some sort of question of, well, should I check the outer or the inner? Should I find an average to check the ratio? Here, it really does not matter because we're not taking it too hard and fast about how we're doing this. So almost no matter what we do, we're going to be okay. In this case, we could take the smaller 68 inches over 2, and that would be 34. That's greater than the 20. So therefore, thin wall pressure vessel theory does apply here for us. So that's good. All right, so now what we're going to do is we're asked to find both the longitudinal and the hoop stresses. Right now, the longitudinal stresses are basically associated with trying to blow the end of this cap off. And so there's your long direction. And the hoop is the circumferential trying to expand this whole thing. So, gee, which way do you want to go? I'm going to suggest that for now, we're going to cut a cross section. I'm going to show it and draw it as though it's close to the end, but it's not. It's far enough away, St. Benot's principle, that this 6 foot, we go in at least 6 foot to cut through in that cross section, okay? And what I'm going to show here is the left half. It's not particularly important which one we do, but there's the outer part, and there's that inner part. There's the other end. Okay, so the pressure, imagine that you've got a thin film across this surface right here, and that content there, you know, it's pressurized. It wants to get out. So across that, you have to impose a large force that's spread out evenly across that. That's that internal pressure, P. That's what our 1200 psi is all about. Okay, and so that pressure times that area is the inner diameter squared times pi over 4. Right, so that's that internal effect. Now, that's going to cause tension around the perimeter, right? And so that's going to be then that resultant is that stress, which is the longitudinal stress times that area. Now here we make a simplification here, that area is related to that circumference. So that would be pi times d times then that wall thickness. It's only an approximation, but it's a reasonable one, especially when the t is much smaller than the d. And the question really does become, well, should we be using DO, DI? Oh, that's an interesting question there. And we're just going to let that sit for just a second. But first, we'll just do a sum of forces. Let's do it in the long direction, take to the right positive. And so we would have sigma L pi dt minus the capital P set it equal to 0. And then we'll have sigma L equals that capital P over pi dt, and then we'll substitute in for capital P our pressure times our inner diameter squared times pi over 4, and then pi dt. Notice that we get some nice cancellations happening. The pi's go away. And boy, it sure would be convenient if we used di here, because we know that that's more exact for this internal pressure effect. And so if we do that one down here, right, it's an arbitrary selection. We get rid of one of those, and we're left in with our model that our longitudinal stress is equal then to our internal pressure times our diameter, inner, over 4t, right? And in this case, then, that would be 1200 psi times 72 inches. Oops, no, it's not. It's 68 inches. That's a common mistake. I actually made it on purpose just to show you what that common mistake is. Well, you can believe me or not, but it should be the internal diameter. So 1200 times 68 divided by 4 divided by 2, and we get 10,200 psi, or 10.2 ksi. From 1.2 psi of pressure, we get a much larger structural stress. That's a good rule of thumb to realize here, that small amounts of internal pressure will create large structural membrane stresses. They're not the same kind of thing, even though they have the same kind of units, and you might sort of think about them the same way. Right, so that was our derivation. That was, sorry, step 2. That was the longitudinal stress. We got a little carried away there. Got excited about the free body diagram and what we were doing. All right, so that's step 3. Now, step 2. Step 3, let's go find then the hoop stress. I'll have to slide up and down on the screen here a little bit. What we're going to do here is we're going to take a slice through the middle of this thing, right? Like a magician, and just cut right through it. We don't care about the ends, so we're going to cut those off too. And when we do that, and let me write one more thing here. We'll call that length L there. Now, you're not going to like that because that looks like longitudinal, doesn't it? All right, we'll call it W instead. All right, I have a cat over here that's yowling a little bit. That's kind of fun for a classroom video in college, huh? So if you hear a little meow, he's got a nice little mouse that he has caught, a toy mouse. My other cat catches real mice. There's that inner surface of our pressure vessel, and there's that outer little piece, right? So we're away from the ends, we've cut through it. The length here that we have is W, and again we have this sort of film, that magic film, and we've got this pressure that's keeping all that content in there. Yes, on the sides too that we just looked at, but we're going to ignore that direction and focus only on what's happening as this thing is trying to blow apart, right? And so this big now force P, that P is going to be that internal pressure times this width times, once again, that internal diameter. Whereas then this resultant in the other direction is going to be our average hoop stress, right? And then the area that we've got here is, oops, not equals, hoop stress times that W times that wall thickness, and there's 2 of those as that resultant, right? So when we sum forces here in this other direction, then we get 2 sigma HWT minus capital P, set it equal to 0, like we did before. And so now we'll get that sigma, the hoop stress, is equal to our capital P over 2WT, and capital P is equal to our pressure times W times DI over 2WT. W's cancel out, and your model for the hoop stress is that it's the pressure, internal pressure, times that internal diameter over 2T. That's twice as big as the hoop stress, right? And so then our hoop stress here would equal then 20,400 psi or 20.4 ksi. Now look at that multiplier. 1.2 ksi of pressure generates 20.4 ksi of internal stress, right? So when we're not done yet, right, because we were asked to find the factor of safety with respect to our yielding. So we'll take our maximum here. Well, this is interesting. 2, our max normal stress, this is quite, if you can hear the cat, he's really going crazy over here. Our stress block then is, we've got sigma h there, sigma long there, and sigma h is equal to 2 times sigma long, right? So more circle then would look like that. We've done this one actually before. We got a specific example on that. So this really, right there, sigma h, is the max normal stress. So when we want to go look at the factor of safety, then we'll take our criterion stress divided by our max, which is the sigma h, and that's going to be your 36 over 20.4, and that should be our 1.76. Let's find out. Ba-bam! 1.76 for our factor of safety for this particular system, right? So the key equations or models that you have developed are the hoop stress model. Oops, I wrote that wrong, didn't I? Sigma h is equal to twice the longitudinal. There you go. So let's rewrite this one more time. Sigma longitudinal is pi d over 4t, and sigma h is the pressure times diameter of 2t. Now you're going to look up this in some reference and you're going to say, you're wrong. That's not a 4, that's something else. Well, sometimes they'll write it in terms of radius, but diameter is equal to 2r, so you'll get that be equal to p times ri over 2t, and then this one will just be pi over t. Ooh, yikes. You got to know which one you're using and what's going on in the specific situation because they look awfully similar to each other. It's not like polar mode of inertia where there's a coefficient of 2 or 32, and it's a lot easier to figure out which one's going on just by observation. You got to know what's really going on and select the correct one here.